In this lesson, we shall look at Physical Sciences Paper 1 out of 100 marks written in 1.5 hours. We start by focusing on the first questions first, but we have multiple choice questions in the beginning. Right, section A, question 1 focuses on multiple choice questions. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write only the letter A to D next to the question number 1.1 to 1.10 on the answer sheet. Each answer counts 2 marks. You can see it's 2 marks there. Right, what is the magnitude of the angle between the direction of the disturbance and the direction of propagation of a transverse wave? Here's a wave that does this kind of motion. And now if you understand, therefore, the wave is actually moving in that direction and it keeps moving up and down, then up, etc. In the direction of propagation, it's that way. So what is the magnitude of the angle between the direction of disturbance and the direction of propagation? Right, we agree that the propagation is towards the right, for example, here, and the disturbance here, you can see it's, for instance, going down. And so what is the angle there? If this is going down, is the disturbance, the direction of propagation is that way. What is the size of this angle here? What is the size of that angle there? Anyone home?
90 degrees.
It is exactly
90
90.
degrees.
It is exactly 90 degrees. So we can see that the angle is 90 degrees there. And that is the actual angle between the direction of the disturbance and the direction of propagation of a transverse wave. Next question. The diagram below shows 2 waves traveling in the same medium for the same length of time. Right, here we have 2 waves that are traveling in the same medium for the same length of time. But these are 2 waves, wave number 1 and wave number 2. Each wave has its amplitude and frequency. The 2 waves have different what? What do they have? Have different what? Do they have different amplitudes? Do they have different speeds? Do they have different energies? Do they have different frequencies? What do they have that is different? Anyone home quickly? Before I give the answer, which one do you think is the correct answer? Please come again.
Frequency.
Okay, that's fine. So, but what we're sure of is that these 2 waves here, if you look at the distance from here to there, is the amplitude. So at this point, you're able to see, therefore, that if you look very carefully, these are not drawn to scale, but you draw a line right through these waves, and you're able to see, therefore, that these waves here themselves, if you go horizontally like this, each one, now, this one here has a smaller amplitude, but this one is a larger amplitude. So what we're sure of is that these 2 waves have different amplitudes, right? Where the amplitude is the distance from the vertical displacement, from the equilibrium position to the highest crest, right? So, and you're able to see, therefore, that here there is some amplitude A1, there's some amplitude A2, and therefore these are different. Okay, so yeah, take note of that. Next point. Next point. So in 1.3, 2 points on a transverse wave that have the same magnitude of displacement from equilibrium are said to be in phase if these 2 points, or rather, if these points have the what? So we're saying 2 points on a transverse wave that have the same magnitude of displacement from equilibrium are said to be in phase if these points have the what? The same direction of displacement and same direction of motion, same direction of displacement and opposite direction of motion. C, opposite direction of displacement. Okay. And same direction of motion. D, opposite direction of displacement and opposite direction of motion. Okay, look at this very carefully and let us know what you think of this. Right, anyone home?
I think it's
Anyone
B.
home? You think it's B? Okay, that's fine. So we're saying 2 points on a transverse wave that have the same magnitude of displacement from equilibrium. So in other words, here's the transverse wave. Now here is equilibrium. And if you do this, and if here are 2 points, right? And obviously, I mean, if we are to then say these points, they might be here, and you have the same distance here, and you have the same distance there. And you are saying 2 points on a transverse wave that have the same magnitude of displacement from equilibrium. Okay, because this is equilibrium. Equilibrium is this, right? So if this is equilibrium, so we're saying 2 points on a transverse wave that have the same magnitude of displacement from equilibrium are said to be in phase if these points have the what? Okay, so you think about
B.
this. Yeah, it's like you want to say something.
I see A.
Well done. A is the correct answer. If they have the same direction of displacement and same direction of motion, same direction of displacement and same direction of motion, and therefore they're said to be in what? They're said to be in phase. So A is the correct answer. A is the correct answer. Next question. If two charges are identical with one having a charge Q, so here are two charges. This one has the charge Q, and okay, there are two charges. Here's another one. This one has charge Q. This one, we don't know. All right, and they are brought together to touch each other and are then separated. Okay, you take these identical. What does identical mean? Identical means they're the same. Okay, they're brought together and then separated. The new charge on each will be what? What do you think the answer is? Anyone home? So you take this one with charge Q, this one has zero charge. Zero charge. And you
A.
bring them, okay, that's awesome. So the new charge on each will be, okay, that's fine if you're thinking so. Let's think about this one. So obviously now, if you bring them together, you'll have to say charge Q, and then you take the charge here, which is 0, and then you divide by 2, because you must add these two charges. So this will give you the new charge. So new charge is the charge Q plus 0 divided by 2, which is exactly Q over 2. And therefore, the correct answer is half, because you will have to take this charge and divide it by 2, because they're going to share the charge. They're going to share the charge, these two objects. They're going to share the charge. So you see, when they share the charge, we divide by 2. Any question? Next point, 1.5. The region in a space where a magnetic material will experience, okay, so I mean I made a typo there, will experience a force is called A or N what? The region in a space where the magnetic material will experience a force. Right, so a magnetic material experiences a force. Right, so in other words, if you take a magnet, and now here's the magnet, and then now we're seeing this here, and now these things here. Okay, is something called a bar magnet? What is a bar magnet? So now a bar magnet with the charge. So you can have a charge on it. And there, for instance, if it is the north pole of the bar magnet, or you can have the south pole of the bar magnet. Right. So what do you have here, for example? This one in the north, where do the arrows go? Where do the arrows go? Where do the arrows go? So the region in space where a magnetic material, so a magnetic material experiences a force in a magnetic field. In a magnetic field. All right. So this experiences a force in a what? In a magnetic field. And therefore the correct answer is this, because you're dealing with a magnetic material. And this magnetic material experiences a what? Experiences a force, and therefore it experiences a force because it is a magnetic material. It experiences a force in a magnetic what? In a magnetic field. Altogether.
Yeah.
Next point. Which one of the following is equal to 10 coulombs per second? Which one of the following is equal to 10 coulombs a second? Is it A, 10 volts, B, 10 amperes, C, 10 ohms, and D, 10 nanocoulombs? Here you're dealing with the volts, and here you're dealing with amperes, and here we're dealing with ohms, and here we're dealing with what you call the nanocoulombs. So tell us which answer is the correct one here. So which one of the following is equal to 10 coulombs per second? Which one? Which one? What do you think? Okay, so obviously, I mean, you are looking at these here. It's 10 coulombs per second, which is the same as what? Which is the same as charge per unit time. And what is this? What formula is this at the back of the exam paper? What is this? Charge per unit time is equal to what? Who knows this formula? There's a formula that says charge per unit time is equal to what? Anyone, what is this formula? Charge per unit time is equal to what? You forgot the formula. Okay, the formula is that electrical current is equal to charge per unit time. This is electric current. So in other words, this one here, and now you know that the electric current is measured in what? Electric current is measured in what? What do we use to measure electric current? Okay, so this one is measured in amperes. Electric current is measured in what? In amperes, because you say there are 2 amps, there are 3 amps, there are 4 amperes, and so on and so forth. And we use something we call the ammeter. We use an ammeter to measure the, right, we use what you call an ammeter to measure the electric current through a conductor. Okay, so in other words, in 1.6, we have that the correct answer is B. It's 10 amperes because it is the examiner said 10 coulombs per second. So 10 coulombs per second. The C is for charge, and this one is change in time, or just time there. Okay, that's something that you need to take note of there. Right. Okay, we continue. Next question. Okay, for which one of the quantities below is the correct unit of measurement for the given quantity? A, the quantity is current, the unit is amperes per second. B, energy is kW, that's like the kilowatt. And C, quantity is potential difference is measured in volts. D, resistance is measured in volts seconds. Which one is the correct answer? Which one is the correct answer? Which one is the correct answer?
D.
Okay, let's think together. Okay, 1.7. 1.7. 1.7. All right, so the correct answer in 1.7 is that potential difference. Like if you know that V is equal to IR. So this is called potential difference. It's called potential difference. And so the potential difference, 1.7, you have potential difference, and potential difference in 1.7 is measured in what? In volts. So the unit of potential difference is V, the volt. It's V, the volt. It's V, the volt. Yeah, we're good. It's V, the volt. So we continue. Next one, 1.8. Consider the following statements concerning ultraviolet radiation. Ultraviolet radiation, that is UV radiation, right, which is ultraviolet radiation. Right, it can be reflected. It has a longer wavelength than gamma rays. It is radiated from the sun and may be harmful to humans. So consider the following statements concerning ultraviolet radiation. Which one is the correct one? So it can be reflected. Is it yes or no? So you need to choose here, because this one, A is Roman figure 1, Roman figure 2 only. B, Roman figure 2, Roman figure 3 only. C, Roman figure 1, Roman figure 3 only. D, Roman figure 1, Roman figure 2, Roman figure 3. Which one is the correct answer? Okay. So yeah, what do you think of
between
this one?
between B and
Okay. That is fine. So we're dealing with 1.8 now, dealing with obviously these particular options, but we know very well that the UV radiation there, they can be reflected. That is true. It has a longer wavelength than gamma rays. Yes. It is radiated from the sun. Yes, UV rays are from the sun, because if you are exposed to the sun too much, they cause sunburn. So some people who stay in the sun in the beach, if you go to Durban, you're in the beach for too long, you're in the sun, you can experience some sunburn because of the UV radiation. They can also, in other words, it is radiated from the sun and may be harmful to humans. It is harmful to humans. Okay. So we have that. We have that. So in other words, yeah. Okay. Okay, we continue. So in 1.8, therefore, the correct answer is option D. So it can be reflected, yes. It has a longer wavelength than gamma rays. That is true. It is radiated from the sun, may be harmful to humans. Yay, it causes sunburn. It actually scorches humans. It affects humans. So the UV rays, you might need some sun cream to make sure that you don't burn too much in the sun. And these UV rays are the culprit. Okay, they really have a negative effect on the human skin. So something to take note of there. Okay, let's get the next one. Choose the correct combinations below concerning the pitch and loudness of sound. Choose the correct combinations below concerning the pitch and loudness of sound. Okay, so the pitch and loudness of sound depend on what? Okay, so now let us look at this one. A is frequency. A is the pitch is frequency. Loudness is amplitude of vibration. B, frequency, and this one is speed of vibration. C, it's amplitude of vibration. And this is loudness, which is frequency. D is speed of vibration. Loudness, which is frequency. So choose the correct combinations below concerning the pitch and loudness. So the pitch and loudness of sound depend on what? So does the pitch depend on frequency? Or does the pitch depend on amplitude of vibration? Or the pitch, does it depend on speed of vibration? Loudness, does it depend on the amplitude of vibration? Does it depend on speed of vibration? Does it depend on frequency? What does loudness depend on? Who thinks they know the answer here? Right. So we continue. We continue.
Okay, nhé. Đây án suy nghĩ mà có. Thì là nó thì các bạn. Ừ.
What do you think?
Thì là nó các bạn thì ít là gì. Eh, gì, yeah. Nhiều.
Okay, the pitch. The pitch depends on frequency. So yeah, it depends on frequency, can either be A or B. But now in the loudness, loudness depends on the amplitude of vibration. So the correct answer is A. So pitch depends on frequency, but loudness depends on amplitude of vibration. So the higher the frequency, the higher the pitch. Loudness depends on the amplitude of vibration. And therefore, in 1.9, we have the correct answer, which is A there. So we continue. We continue. Next question. Two pulses travel towards each other as shown in the diagram. Okay, there's a pulse that is traveling towards this side, towards the right, and this one is traveling towards the left. When they meet, the resultant displacement and type of interference will be what? So because this one has amplitude A, but this one has the resultant displacement, which is A. So now the resultant displacement is going to be what? When they meet, will it be 4A, 2A, minus 2A, minus 4A? The type of interference, will it be constructive, constructive, destructive, destructive? So which one do you think is the correct answer? I'm testing you here before I give you the answer. What do you think in 1.10? What do you think in 1.10? What do you think in 1.10? Please come again.
A.
Okay, that's fine. That's okay. Anyone home? Anyone home? Right. So what we can see that this one is 3A and this one is A, amplitude wise. So, and obviously we can see that this one is on the bottom side, this one is on the negative side. So it's A minus 3A and this is minus 2A. So this is like a plus, and you can view this on the minus side. And obviously if they meet, then doesn't matter. Yeah. Okay. When they meet, then is like A minus 3A, which is minus 2A. So minus 2A is the correct answer. But obviously in the end, because of the fact that there are different magnitudes, what then we're seeing here most certainly is that we have different destructive interference. We have destructive interference. We have destructive interference because these are not certainly in phase with each other. They're not certainly in phase with each other. So we're looking at 1.10. 1.10. So let's look at the next thing. Okay, question. Now we're looking at section B. So section B now is about waves, and we have waves in detail. Let us answer the questions on waves as you'd be required to answer in the exam, in the June exam. The diagram below shows two waves, A and B, of the same wavelength but different amplitudes. Two waves, A and B, of the same wavelength but different amplitudes, crossing each other. Okay, so you have the position, which is in meters, and you have position versus time, and you have the time. Now define the term wavelength. Define the term wavelength. Define the term wavelength. Let us define the term wavelength. Right. So what is wavelength, guys? Anyone home? What is wavelength? Anyone home? Who knows what wavelength is? Let us define wavelength. I don't know if anyone knows what wavelength is. Who knows? Right. Okay, wavelength. Okay, we define wavelength and you say, right, wavelength, right, is the distance. So wavelength is the distance. So this is how we write. You say wavelength is the distance between, right. So it is the distance between two consecutive, right. So in other words, we're looking at the distance between two consecutive or successive, consecutive or successive points, okay, consecutive successive points in phase, in phase. So now we're saying wavelength is the distance between two consecutive or successive points in phase. Right, so this is what we get. Wavelength is the distance between two consecutive or successive points in phase, and this is what we call wavelength. So we have defined the term wavelength. So it's something you need to take note of. Let us look at the next question. Let us look at the next question. Right, so in the next question, we shall look at this, and they're saying, draw the shape of the resulting wave. So yeah, let's just look at these here. So draw the shape of the resulting wave as the two waves A and B cross. On your diagram, show the resulting amplitude. Draw the shape of the resulting wave as the two waves A and B cross. On your diagram, show the resulting amplitude. Right, so yeah, take note of this. What are you supposed to do? You need to draw the shape of the resulting wave as the two waves A and B cross. Okay, here are these waves, A and B. And now as they cross, we are then saying we need to draw the shape of the resulting wave as the two waves cross on your diagram. Right, show the resulting amplitude. This one is amplitude A, for example, which is wave A, and wave B has amplitude B. So, and obviously you can see this one here, it's A here, and it's minus A there, and this one is minus B over there. And we're then saying in the end, we need to draw the shape of the resulting waves as the two waves A and B cross. When your diagram show the resulting amplitude, right? So let us look at that. But you really can see the pattern there. Let us continue there to draw. Right, so to draw that, we have the following. So we're going to draw here in the, here. Okay, so if then you have these horizontal axis. So yeah, you can draw it there, but you can draw it anywhere. Let's draw it somewhere here. Let's draw it somewhere here, like so. And then you draw on the vertical like this. You draw on the vertical like this. And then now you're gonna see this is gonna go up like this. Okay, it's gonna go up like this. Okay, let me just try to draw carefully. It's gonna go up like this. Gonna go up like this. Right, gonna go up like this. Something like this. Okay, so that in the end, then you have position here. Right, we have position here in meters. And then now you're going to have this one here, which is exactly A plus B with time in seconds. Oh, yeah. This is what we have. So this is the sort of rough graph we're going to have, because you really can see that these are in phase with each other. Since they're in phase with each other, because you can see the crest and the crest sort of on top of each other, and therefore you can see here the trough and the trough are on top of each other. So you're gonna add the A and the B, so they're gonna sort of amplify each other. So draw the shape of the resulting wave as the two waves A and B cross on your answer. Right, on your diagram, show the resulting amplitude. So yeah, they'll sort of amplify each other, and therefore they will have a greater amplitude. So you'll have to add the amplitude of A and the amplitude of B. Okay, so take note of that. Let's look at the next question. Which wave property is illustrated in question 2.1.2? Which wave property is illustrated in question 2.1.2? Which wave property is illustrated in question 2.1.2? Okay, yeah. Who want to answer that one quickly? If they ask you this in the Jude exam, what are you going to say? What is the wave property that is illustrated in question 2.1.2, where we drew the graph? What is the wave property there? Anyone who knows? I'm testing you.
Longitudinal curve.
Okay, that's fine. That is fine. That is fine. So the wave property in 2.1.3, it is called the wave property is called superposition. It's called superposition. If you don't want to say superposition, you can say the constructive interference. Constructive interference.
Why or superposition?
Why is it superposition? It is superposition because we are adding the amplitudes. Okay, because now we're able to see here the amplitude of the first one is A, and the amplitude of wave A has amplitude A, and wave B, which is higher here, has amplitude B. And so what we can see here as a consequence is therefore that the two amplify each other. They increase because these are in phase. Okay, so the kind of the wave property here is that which is superposition. And superposition, because they are in phase with each other, so we're going to have that this crest and the crest are on top of each other, the trough and the trough are on top of each other. So we have what you call the constructive interference. Okay, so if we have constructive interference, we say the superposition. Superposition means that you add the amplitude A and B. So you're going to have a new amplitude A plus what? A plus B. Okay, right. So that is the wave property. So the wave property in 2.1.3 is what you call the superposition. And superposition has to do with constructive interference, or yeah, if you want to say superposition, you say constructive interference. Why is it constructive interference? Because these two waves are in phase. How do we see that they're in phase? They're in phase because you have crest, crest, trough, trough, crest, crest, trough, trough. Let's look at 2.1.4. 2.1.4. State the principle used in 2.1.2. Okay, 2.1.4 is saying state the principle. State this principle. Let's give a statement of that principle. What is the statement of that principle? Okay, this is the statement of the principle. The statement of the principle says the following. So it says when two waves meet, when two waves meet at a point, when two waves meet at a point, the resultant disturbance, the resultant disturbance is the algebraic sum of the two algebraic sum of the two waves. When two waves meet at a point, the resultant disturbance is the algebraic sum of the two waves. That is the superposition principle. That is the superposition principle. Okay. And this superposition principle says when two waves meet at a point, the resultant disturbance is the algebraic sum of the two waves. So here is this one. They meet. This one is A and that one is B. So when they meet, then they're going to have a higher thing like this. So because now this is going to be A plus B. So it's going to go up like this, A plus B. And then now also this one is going to go like this. So it's going to be minus A plus B. Or you can say here it's going to be like minus A minus B. Right, minus A minus B. And then this one, because it's A here and then B there, it's going to go like this. Okay, so this is called superposition or constructive interference. So they sort of amplify each other. And therefore, you have A plus B here. Like that. And this one is minus A minus B. Right, so yeah. State the principle used is exactly that. Okay. What is the superposition principle? It says when two waves meet at a point, the resultant disturbance is the algebraic sum of the two waves. The resultant disturbance is the algebraic sum of the two waves. That is called the superposition principle. So we continue. And here's another question. In the sketch below, not drawn to scale, Q represents an object on the surface of the water in a dam. Okay, so this one represents an object on water. So this is an object on water. So yeah, this is an object on water. Okay. A person standing on a bridge observes object Q moving up and down. A person standing on a bridge, observes object Q moving up and down. Object Q rises to the top every 5 seconds. It rises to the top every 5 seconds. It rises to the top every 5 seconds. Define the term period of a wave. What is the period of a wave? Okay, what is period? What is period? Who knows? Please come again, Mpo.
Time taken to complete one wave.
Well done, well done. The time taken. We refer to the time taken to complete. Time taken to complete a single time taken to complete a single oscillation. Time taken to complete a single oscillation. This is called a period. Period means the time taken to complete a single oscillation. That is a period. Okay, next question. 2.2. In which direction is object Q about to move? Right only, upwards, or downwards?
Upward.
Okay. So because it's moving like this, and then here, okay, here is already moving down. So it's moving like upwards, upwards, upwards until it reaches the turning point. At the turning point, it starts moving down until it reaches the turning point. Then it starts moving up. But you can see, because no, it is still moving down, 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 because it must follow the wave like this, isn't it? It must follow the wave like this. So, but because it must follow the wave, what do you think? Is it going to move down or up for it to follow the wave? Is it up or down like this?
Down.
Is it down? It is downwards. Well done. So it is exactly downwards. It is exactly downwards. Because for it to follow the wave, it's going to move down and then up. So it's going to move down and then up. Next question. Calculate the frequency of the waves. Calculate the frequency of the waves.
Kupabusa ng
Yes,
formula
please.
ya the frequency I see F equals 1 over T.
Well done. Frequency Q1 over time. Correct. Right, so to calculate the frequency for 2.3.1, you're going to say frequency is 1 over the period. Right, so frequency, it's 1 over time. So we do frequency as 1 over time, and this is equal to what? 1 over, and we're able to see. Okay, yeah, what is the time?
5 seconds.
5 seconds. Well done, because this is moving up. The object rises to the top every 5 seconds. You can see that the period is 5 seconds. So that if you divide 1 by 5, you get 0,
1,
2 hertz or per second. So you can say 0,2 hertz, you can say 0,2 per second. So that is what we have there. 0,2 hertz or 0,2 per second. So that is what we get, 0,2 per second. Okay, so yeah, that is what we have. And then you look at 2.3.2. 2.3.2. Calculate the speed of the waves. What is the formula for calculating the speed of a wave? What is the formula for calculating the speed of a wave? What do you think, Paul? How to calculate the speed of a wave? What is the formula for finding the speed of a wave? The speed of a wave is the wavelength multiplied by the frequency. Right, so the speed is wavelength multiplied by the frequency, which means therefore the wavelength is 1,5. 1,5 multiplied by the frequency. We got the, what is the frequency? We got the frequency to be 0,2 hertz. 0,2 hertz or 0,2 per second. So we put here 0,2. And therefore, we know very well, therefore, that the actual speed of the waves, it's going to be 1,5 times 0,2. We can use our calculator to do that one. We can use our calculator to do that one. And we have exactly this calculator. So on this calculator, so we're going to take 1,5 multiplied by 0,2, and the answer is exactly 0.3. So it is
0,3.
It is 0.3. Well done. So we have exactly 0.3 meters per second. And this is the speed of the waves. So the speed of the waves is given by 0.3 meters per second. Remember, it is speed and therefore it is without direction. So we only give the magnitude or the size. Okay, so we continue to the next question. Continue to the next question. Right, question 3, a section of a sound wave produced by musical instrument is shown below. Okay, there's a sound wave that is produced by musical instrument and is shown below. And so define the term pulse. What is a pulse? What do you think, Mpo? What is a pulse? Okay, that's fine. A pulse is a single. A pulse is a single disturbance. A pulse is a single disturbance. Okay, so we have therefore that a pulse is a single disturbance that occurs in a medium. A pulse is a single disturbance that occurs in a medium. All right, a pulse is a single disturbance that occurs in a medium. So that is a pulse. Next question. Identify the components. Identify the components of the wave labeled B. Right. B. What is B there in the diagram? What component? What do you think B is? B. Right. What is it? Because this is a sound wave produced by a musical instrument. What do you call B in the diagram? Yes, okay, that's fine. That's fine. Remember, I'm just testing you. I'm just testing you. Right. So B is called the wavelength. B is called the wavelength. Right. So you remember what wavelength is because you are moving it from a region. So it's like a region of uniform spacing, and a region of uniform spacing. So it is called the wavelength. It is called the wavelength. So, right, that is something that you need to obviously take into account, but very, very seriously. So take note of that. Right. So we continue. We continue and we look at more of these things. We look at more of these things. So now, if you look at, for instance, if you look at the notion of what you call a transverse wave, right, a transverse wave, right, and you have the equilibrium position like this, okay, and this one is crest, this one is crest, and therefore the distance there is called the wavelength. It's called the wavelength. So yeah, this one, same uniform spacing. So we have what you call this B is going to be called the wavelength. Wave, right, it's going to be called the wavelength. Right, it's going to be called the wavelength. Just take note of that, wavelength. Right, wavelength. Right. So from crest to crest to from trough to trough is called the wavelength. All right. So yeah, take note of that and we continue. We continue to look at more things that matter. We continue to look at more things that matter. Let's look at the next thing. The next thing. What is A? What is A called? Now here is A. But you can see here, this A is below uniform spacing, uniform spacing, uniform spacing. And now we can see that these are like closer to each other. Closer to each other and closer. And here there is wider spacing, but here they're closer to each other. And A is actually called compression. A is called compression. Right, it's called compression because they're closer to each other. Okay, so we continue. We continue. So in other words, this one is called compression. And this one is also called compression. And also that is called compression as well. And that is
The
called the wavelength.
compression because kopane
Yeah, because yeah, the copper and these the sort of the crest of the wave. So obviously this is an example of a wave that so there are compressions. Then what do you call these ones? These ones. Now, if you can put a C here, what is C now when they are far from each other? When they are far from each other, okay? We call them rarefactions.
reflection.
Yes, we call them rarefactions. Right. Now, the rarefactions means that they are far from each other. Rarefactions means that they are necessarily far from each other. And so we are able to then say that there is, now if you look at the spacing here, we're able to measure a full cycle, like one cycle can be measured from here to sort of there. We measure a full cycle, right? From the density to the density, we can be able to measure a full cycle. Where they're closer to each other, we measure a full cycle, and here, between here and there, we measure a full cycle as well. Okay, take note of that. Okay, that was 3.2 point. So yeah, that's the compression A, and obviously B is called the wavelength. Let's move to the next one. The highest frequency that a normal human ear can hear is about 20 kilohertz. A special whistle known as the silent whistle is used to train dogs. Something called the silent whistle. Here's the whistle used to train dogs. Right, so we continue to then say, if the whistle produces sound waves, if the whistle produces sound waves of a wavelength 9 millimeters, determined by calculation whether the human ear will hear the sound produced by this whistle, take the speed of sound in air to be 342 meters per second. Right, so yeah, you determine by calculation. So what do you think we need to do there? What do we do there? You calculate a, well done. You calculate a frequency, and so now what formula do we use? Okay, y'all, that is we're gonna use speed equals frequency times the wavelength. And
Yeah,
then you
and
already,
then
yes. And then we plug it. Yes, my dear. All right, my dear. Okay, yeah, just 1 minute. Think about it. I'm coming now. Cool. All right. Okay, thank you, my dear. Thank you, my dear. Right. So we continue. We continue, Poya. So what do you think?
yeah, it was also
Mm-hmm.
I don't know what formula to give you equals to um frequency times wavelength. And then
Yes.
at what point and then we go on 342 equals to wavelength times 9.
Well done. So 342 key speed is equal to
Yeah,
wavelength
and then
because we have our data. So the data is that the speed is 342 meters per second. And then the wavelength, what? What is the wavelength?
9.
The wavelength lambda is 9 millimeters, but you must convert it to meters. So how do you convert millimeters to meters? We divide by 1,000. Divide by 1,000 meters. So that in the end, then you have the substitution that you're supposed to do here. So you have this one, and if you divide by 1,000, you can even use a calculator to see what's going to happen here. Let us use our calculator.
Naya ka is
Calculator. Okay, yeah, how we ring. Okay, let us do this
impa
together. So if you,
what's
I wanted to do this one. So if you then say 9 divided by 1,000. So 9 divided by 1,000 is equal to what? Which is 9 times 10 to the minus 3, right? Right, so that is okay. So you'd have therefore that this is 9 times 10 to the minus 3 meters. 9 times 10 to the minus 3 meters. So yeah, then what do we do at this point?
and then you transpose.
We transpose, so we have 342. You divide by 9 times 10 to the minus 3. Okay, you can leave the units out of it. Can leave just the units out of it. So we divide both left and right by f times 9 times 10 to the minus 3. Okay, and then you also divide here by 9 times 10 to the minus 3 in October. Right. Yes, right, lap. Okay. Yeah, I'm in class now. I'm just doing physics until 8 with some students online. Okay. That's fine, but I'm gonna check on you when I'm done with my class. Okay, at 8. Okay. After 8, I'm gonna. Okay. Okay, sharp, sharp. Right, so this one here cancels
And
the
then yeah, cancel
cancel and then now, but they got divided this one. So you're gonna have here you have 342 divided by 9 times 10 to the minus 3, which means F equals. Uh-huh.
Kira pa 28,000.
Uh-huh. Okay, Humana, what you get as your answer? So if you have 342 and you divide that by 9 times 10, right, to the exponent minus 3, and you're getting exactly 38,000. 38,000 hertz. Right. So what we're then getting is exactly 38,000 hertz. 38,000 hertz is the same as exactly 38 kilohertz. Right. So, but the 38,000 hertz is actually bigger than 20 kilohertz. So it's much bigger. And the normal we can hear the highest frequency is 20. So it means therefore the humans cannot hear this sound. It means that humans cannot hear this sound because the largest people can hear is 20 kilohertz. So now this one is 38 kilohertz because the 1,000 is kilo. 1,000 is what? Is kilo. Okay, so it's 38. 38,000 hertz is like 38 kilohertz. So yeah, 38 is bigger than 20. So 28 kilohertz is bigger than 20 kilohertz, so that yeah, the humans cannot be able to hear this kind of sound. Next question. Next question. So yeah, okay, let's look at 3.2. Name the type of sound produced by the silent whistle. What is the type of sound that is produced by this silent whistle? The type of sound that is produced by the silent whistle, what do you call it in Poe? It is called ultrasound. It is called ultrasound. It is called ultrasound. It is called ultrasound. Because why it is ultrasound? Because it is the kind of sound that the humans cannot hear. And in this case, it is 38 kilohertz, and humans cannot hear this kind of sound, and it is ultrasound, which is certainly bigger than 20 kilohertz, and we call this ultrasound. Okay, let's look at the next one. Okay, now a sound emitting device is placed between two buildings A and B as shown below. Here's building A and building B, and obviously you have there's a device between the two buildings. A sound wave emitted from the device strikes building A and perpendicularly returns to the device after 1,0 seconds. A second sound wave strikes building B perpendicularly and returns to the device after 1,5 seconds. If the speed of sound in air at that point is 340 meters per second, calculate the distance between the two buildings. Calculate the distance between the two buildings. So yeah, this is one question you can do. So we're going to calculate right now first the distance from device to building B. So we're going to look here at the distance from device to building B. Okay, and that distance is S equals VT. That distance is S equals VT, use this formula. So which means S is equal to, we use 340 meters per second, we multiply by the time. So, right, so obviously we have a couple of times here, and we need to take note of that. Because a second sound wave now strikes building B perpendicular and returns to the device after 1,5 seconds. Okay, So if it is after 1,5 seconds, right, and then this one, so it's 1,5 seconds it returns. So you must then say 1,5 seconds divide by 2, and then it is 0, so the time there is 0,75. So you put here 0,75 seconds. And then it is exactly, the 340 times that will give us exactly 255 meters. Now there's also what we call the distance. The distance from device. From device to building A. So that S equals VT. So which means that the speed is 340 of the sound, but the time now for the device strikes building A perpendicular and returns to the device after 1 second. So which means the time associated with A and this one associated with B, this one associated with A is going to be 1 divided by 2, because you are thinking about the return. So the device, it goes and it returns. So now you must take the time and divide by what? So it goes and it returns. So if it returns, then everything is in 1 second. And here is 1,5 seconds. Okay, so now if everything is actually in 1 second, and here it is 1,5 seconds, you divide by 2, which is 0,5 seconds, which is 0,5. And therefore, this is actually 340, and you multiply it by 1/2, which is 170. 170 meters. So now then here, you're going to say for the building A, you are dealing with 170 meters, and here 255 meters. And therefore now the distance,
Why would it divide
ka 2. Because they return, so they travel twice. So, but direction A1, because obviously at the end, the device is emitting the sound emitting device, sound emitting. So the sound that is going to come from the device to A and then back. But remember, I want to calculate the distance between the two buildings. So if we want to find the distance between the distance from here to there, we can't say the distance from the device to the building is the distance here and then back, because you travel twice. So, but we want one direction, the distance from here to there, not going back. So that in the end, then the time here is 1 second. If it's 1 second to go and come back, what is the time to go only and not come back? Because we want the time from here to there. Because the 1 second is to go and come back. Then if it is to go only, you must divide by 2. Because so that you just divide this by 2. Okay, and then you then come and then say this point, distance between two buildings. Distance between two buildings. Distance between two buildings. Okay, the distance then it's 255. It's 255 plus 170. And the 255 plus 170 is equal to what? Right, so you have 255 plus 170, and that is 400. 425 meters. So which means here it's 170 from the device to building A and 255 meters from the device to building B. Then the total distance is 170 plus 170 plus 255, which is 425 meters. Let's wait the next question. Right, radio waves are observed to have a wavelength of this much. So we are dealing with radio waves to have a wavelength of 0.14 meters. Right, give one use of radio waves in technology. What are radio waves used for in technology? So we're looking at 4.1.1. What are radio waves used for in technology? What do you think? So we know that radio and TV broadcast, radio and TV broadcast. Okay, so the radio waves in technology are used for radio and TV broadcast. So they're also used for communication. Right, they're also used for communication. They're also used for locating information. Locating information about our universe. Sure, yeah. They are used for the radio waves in technology, radio and TV broadcast, communication, or locating information about our universe. Anyone, yeah. But radio and TV broadcasts are the most popular uses of radio waves in technology. 4.1.2, calculate the energy of a photon. What is the formula for calculating the energy of a photon, Paul? Energy of a photon, what is the formula?
So, formula is
Please come again.
the formula is
Okay, that's fine. So energy of a photon is HF. E equals HF. This one is HF like that. So we know therefore that H is 6,63. H is 6,63 times 10 to the minus 34. Okay. And so we are then interested in the frequency. So what is the frequency? We know that the speed is frequency times wavelength. We've been given so we're going to put here speed over frequency. Yeah, speed over wavelength is frequency. Right, so we're going to put here speed over wavelength. That is frequency. Right, so that in the place of frequency, you put speed over wavelength, which is 6,63 times 10 to the minus 34 multiplied by what is the wavelength? 0,14. No, that is the speed. Remember that we are dealing with a photon. So a photon of light, for example. And what is the speed of light? V, the speed of light in vacuum. What is the speed of light in vacuum? The speed of light in vacuum is 3 times 10 to the 8th power. And the wavelength is 0,14. And if you use a calculator here, it becomes 1,42 times 10 to the minus 24 joules. Times 10 to the minus 24 joules. Like that. Okay, energy is measured in joules. Okay, so just take note of that. So you can be able to calculate the energy of a photon of light. So in other words, this is the speed of light in vacuum, which is 3 times 10 to the 8th power. Next question. An athlete breaks his leg while jogging and goes to to have X-rays taken. Okay, one leg is broken of this athlete. The X-rays emitted by the X-ray machine have a wavelength of 1,5 times 10 to the minus 11 meters. Right, so they are the X-rays that are emitted by the machine with a wavelength of this much, which is lambda. Right, so at what speed do X-rays travel? At what speed do X-rays travel? 4.2.1. So X-rays travel at the speed of light in vacuum, which is 3 times 10 to the 8th power meters per second. So y'all, at what speed do X-rays travel? 3 times 10 to the 8th power meters per second. Calculate the frequency of the wave. Calculate.
Something.
Yes, please.
Wing that I 3 times 8 to the power of 3 times 10 to the power of 8.
Yeah, that's a good question. This is a constant. It's always like this. It's always 3 times 10 to the power of 8. It is a constant, and it is the constant. It is the speed. It is the speed of light in a vacuum. It is the speed of light in a vacuum. It is always the speed of light is 3 times 10 to the 8th power meters per second. Okay, so we call it C. We call it C.
Oh.
Yeah, it's there. It's given at the back of the question paper. Always, they must give it to you.
So, but I would that let's say that like question like different now, but what of it is it's a man it's kakana. Okay, one of these.
Hey, you just write it like that. Okay. You just write it like that. Remember that our discussion is recorded, so you'll get quality sound when you receive this video. Okay. Right. So let's look at the next question. 4.2.2, calculate the frequency of the wave, because I can see that our time is running. What if 10 minutes? Might not even finish, but yeah, let's just cruise quickly. Calculate the frequency of the wave. So now, want to calculate the frequency of the wave. So we're going to use the formula. We know to calculate the frequency of the wave. We know that there is the formula. We said that V equals F lambda, where this is speed, but it's F lambda. For the speed of light, V is replaced by C. And then C, we know that is 3 times 10 to the 8th power. And then this frequency is what? Okay. We want the frequency, but you already know the wavelength. Frequency, but you already know the wavelength is 1,5 times 10 to the minus 11. And therefore, you have 3 times 10 to the 8th power, which is 1,5 times 10 to the minus 11. You divide by 1,5 times 10 to the minus 11 divided by 1,5 times 10 to the minus 11, which means the frequency, which is 3 times 10 to the 8th power divided by 1,5 times 10 to the minus 11. And if you divide everything, is 2 times 10 to the 19 hertz. So the frequency of the wave is 2 times 10 to the 19 what? Hertz. Okay, yeah, I'm trying to make sure that we finish at 8. Okay, it's just a few minutes left. Right, so in 4.3 right now, we continue to then say, overexposure to X-rays can be potentially dangerous. Provide reasons for this statement. So yeah, there's a typo here. It should not be provide a reason for this statement. It should be provide a reason for this statement. Okay, obviously at this point, overexposure to X-rays can be dangerous. Why? Why are X-rays dangerous? Why? So we say they are a high frequency. They are a high frequency or energy type. Energy type. They high frequency or energy type. high frequency or energy type of electromagnetic radiation. Electromagnetic radiation with a relatively high penetrating ability. High penetrating ability. Okay, so the high frequency or energy type of electromagnetic radiation with a relatively high penetrating ability. Let us look at the next thing. Okay, question 5. Two insulated graphite coated polystyrene spheres A and B are suspended from threads. The spheres are held apart at a small distance. The charges on the spheres A and B are -8 coulombs and 20 coulombs respectively. When the spheres are released, they move towards each other. Explain why these spheres move towards each other when they're released. Why do they move towards each other when they're released? Paul, what do you think? Why? Why do they move towards each other when they're released?
Because A1 in a
Yes, the spheres. Yeah, okay. So the spheres are carrying. The spheres are carrying. The spheres are carrying opposite charges. They're carrying opposite charges. Okay, these spheres are carrying opposite charges. Yeah. And will attract each other. They're carrying opposite charges, and this will attract each other. Will attract each other. They're carrying opposite charges and you attract each other. Next point. Okay, let's look at 5.1.2. Which one of the two spheres has excess electrons? Write down sphere A or sphere B. Which one has excess electrons? Which one has too many electrons here? Either A or B, which one?
A.
Well done. It is sphere A. Why?
Because it's negative.
Because it's negatively charged. It's negative. Okay. Right. So the two spheres are now allowed to touch each other and then separated. So they're allowed to touch each other and then they're what? They're separated. Okay. So calculate the charge on each sphere after contact. What is the charge of each sphere after contact? So we're going to have Q nu. So if they're brought next to each other and then separated, there's QA, QB, you divide by 2, and the QA is -8, the QB is 20, you divide by 2. And what is this? This is actually 6 nanocoulombs. Yeah, so it's 6 nanocoulombs, and the charge on each sphere after contact. So we're going to have a new charge, Q nu, which is actually +6 nanocoulombs. Okay, let's look at 5.2.2. Will the force now be one of attraction or repulsion? Give a reason for your answer. Okay, because now they will have the same charge, so there's going to be repulsion. There's going to be repulsion. Give a reason for your answer in terms of why. Repulsion, the spheres are now carrying the same charge. the same charge. They are both positively, they're both positively, or if you don't want to say positively, say they're like charged. They're like charged, and they are, okay, and they repel, they repel each other. They repel each other since like charges repel. Like charges repel. Okay, let's look at 5.2.3. State the principle of quantization of charge. What does the principle of quantization of charge state, Paul? Principle of quantization of charge, what does it state? Okay.
As the principle of charge quantization.
Okay, that's fine. So every charge in the universe, this is the principle. Every charge in the universe is a scalar. Is a scalar multiple of the, every charge in the universe is a scalar multiple of the charge of a single electron. Every charge in the universe is a scalar multiple of the charge of a single electron. Every charge in the universe is a scalar multiple of the charge of a single electron. Okay, that is the principle of quantization of charge. Next question, 5.2.4. Determine the number of electrons transferred between the two spheres during contact. Right, so to find the number of electrons transferred, we use the formula. What formula do we use for the number of electrons, Paul? Is the change in charge divided by the charge on one electron. And when these were brought next to each other, there was a transfer of charge. And we know very well that when they were brought next to each other, we had the following. Right, so you're gonna have the transfer of charge. Right, so the transfer of charge is gonna be, so it's gonna be exactly 6 minus 20 divided by minus 1,6 times 10 to the minus 19 coulombs. And therefore, this is exactly 8,75 times 10 to the 19 electrons. If we don't want to do it like this, you can say also, you can say the number of electrons transferred will be the change in Q, change in divided by the charge on one electron. Okay, the final one became 6, and we subtract one of these. Okay, and then you divide that by the charge, which we divide by 1,6 times 10 to the minus 19 coulombs, and the N is going to be exactly the same thing, which is exactly 8,75 times 10 to the power 19 times 10 to the power 19 coulombs. times 10 to the power 19 electrons, electrons. So this will give us the number of the electrons, to continue. The number of the electrons, Next point. Right, so here we consider the circuit below. When the switch is open and the voltmeter is connected across the battery, it reads the EMF of the battery. Right, when the switch is open. Right, consider the circuit below. When the switch is open, here is the switch and it is open, and the voltmeter is connected across the battery, it reads the EMF of the battery. When the switch is closed, the ammeter A1 reads 5 amps. And the ammeter A2 reads 3 amps. Calculate, define the EMF of battery. What is the EMF of a battery? What is the EMF of a battery?
The total amount of electrical energy that a system supply.
Yes. So in other words, here we can say it is the maximum. The maximum energy that a battery can what? That a battery can supply. Can say that, yeah. That's excellent. The maximum amount of maximum energy that a battery can supply is called the EMF. There. Okay, and also there are many ways you can also say it is the maximum. It is the maximum. Maximum energy. Okay, let's see that one. It is the maximum energy that a battery can dissipate, per coulomb. The battery can dissipate per coulomb of what? Of charge. Per coulomb of charge. All right, so yeah, that's what we have. Okay, we continue. So 6 points. The next one is 6.1.2. Calculate the effective resistance of the combination of the two resistors. Okay, so to find the effective resistance, we then say 1 over the resistance is 1 over R1, 1 over R2. 1 over the resistance is 1 over 6 plus 1 over 4. 1 over 6 plus 1 over 4. 1 over R, which is exactly 5 out of 12. R, it is 12 out of 5. And 12 out of 5 is 2.4 ohms. So yeah, the effective resistance is 2.4 ohms. 2.4 ohms. Yeah, just take note of that. 2.4 ohms. Right, so yeah, that is exactly 2.4 ohms. Okay, I'm finishing physics now. Perelelo. I'm just rounding up this physics, and then we're going to start. Okay, so yeah, so we have to calculate the effective resistance of the combination of the two resistors, and it is actually 2.4 ohms there. And these obviously are in parallel with each other. And remember that this is when the switch is closed. So yeah, it's open now. And obviously if it's open, then we assume there's no current that is passing through, because electrons don't jump through an open switch. But once the switch is closed, then we shall have electric current flowing through. Okay, now let us look at 6.1.3. What will be the reading on ammeter A3 when the switch is closed? Ammeter A3, there is a reading there. Okay, obviously we agreed that the switch is closed. And so what will be the reading on the ammeter there? So the reading on the ammeter, you're going to say that it is exactly the following. We know very well that the total current through A1 is 5 amperes. And therefore, if you want to get the current through A3, you're going to subtract the 3. We're going to subtract the 3 amps because, in other words, this one is this plus that is 5. So which means that it is 2 amperes. Right. So it is 2 that you can add to 3 to get 5 there. Okay. So that's what we have. So the through I3, it is exactly the current, which is 2 amperes. Next question. 6.2.1. Consider the circuit below when the switch is closed. Okay. All right, we continue. Okay. Consider the circuit below when the switch is closed. The voltmeter V1 reads. Good. Right, consider this the circuit below when the switch is closed. Voltmeter V1 reads 4 volts and V2 reads 1,6 volts and V4 reads 1 volt. Calculate the effective resistance of the combination of the 3 resistors. 6.2.1. 6.2.1. Yeah, numbers. So we're going to be starting at 8:30 because I'm running late now. I'm just finishing this physics here. Okay, right. So yeah, we're going to be starting at 8:30, and I'm going to send another link at 8:30 because I'm just finishing this physics for grade 10. So the effective resistance now, you're going to have this, that, and that. So the effective resistance for 6.2.1 is going to be exactly R1, R2, R3, because these are in series with each other. Okay, these are in series. This is the formula we use for series combinations. And this is the formula that we use for parallel resistors, parallel resistors with some resistance. And therefore, and this one is for series. So we're going to have 5 plus 7 plus 8. What is 5 plus 7 plus 8? What is 5 plus 7 plus 8, which is 20? 20 ohms. Right, so obviously we want to calculate the effective resistance here that we have for the combination of the 3 resistors is 5 plus 7 plus 8, and it is actually 20 there, 20 ohms. And then now we're looking at the next question, which is actually 6.2.2. Right, so in 6.2.2, we want to calculate the voltmeter reading on V3. The voltmeter reading on V3. Right, so the voltmeter reading on V3, this one. What is the voltmeter reading? If the resistance here is 7 ohms, what is the voltmeter reading on V3? So we can find the voltmeter reading by saying that we have the total potential difference across the battery, which is 4 volts, and then we subtract the 1 volt, and we also have 1,6 volts, and therefore this is 1,4 volts, like that. So we say from 4 we subtract 1 and 1,6 to get V3. So V3 is 1,4 volts. Yeah. So to get V3, we know that our V3 is given by V equals 1,4 volts there. All right. So we look at the next question. 6.2.3, I'm trying to finish off. Right, if the current passing through the 8 ohm resistor, 8 ohm resistor is 0.2 amperes, what will the current through the 5 ohm be? What's the answer? What's the answer? The current flowing through the resistors is given by what? Okay, if the current passing through the 8 ohm, okay, the current passing through the 8 ohm resistor is 0.2 amperes. What will the current through the 5 be? Okay, so yeah, it is in 6.2.3, it is exactly the same, 0.2 amperes. Why? The current flowing, through resistors. The current flowing through resistors in series is the same. The current flowing through resistors in series, because these are in series, so it is the same current there. Positive, negative there, and the current flows like that. Okay, now let's look at 6.3 when we are supposed to calculate charge. Right, in 6.3, the charge of 48 coulombs flows through a circuit in 2 minutes. I'll calculate the current flowing through the circuit. So we have a charge of 48 coulombs. The change in time is 2 minutes. All right, so 2 minutes are actually equal to 120 seconds. We use the SI unit of time. So want to calculate the current, we said I gave that formula for current. So current is charge per unit time, and the charge is actually 48 coulombs per unit time, which is 120 seconds, and you divide these things, which is 0.4 amperes. Right, so yeah, and this is the end of the science discussion. We're looking at a science paper written in 2019. I must thank you so much for joining us. And yeah, it was awesome. Until tomorrow, have a good evening. We're starting at 8:30, Nombuso. Okay, 8:30. I'm sorry I ran late. We're supposed to start at 8, but I'm gonna make it. I'm gonna send another link. We're gonna start at 8:30. Okay. Right. From us, thank you
No
guys.
problem.
Yeah, thank you guys. Goodbye for now.